Howdy, howdy, this is Mr. Potter. Today we're going to be talking about the difference quotient and also how to calculate instantaneous rate of change when given a function. So I want to start from last time. Last time we were dealing with the situation where we were falling with our distance being equal to 16t squared in feet, where t was equal to the number of seconds we'd fallen. And we noticed a couple of things. We noticed that if t was equal to 1.5 seconds, and I wanted to know how far I'd fallen from 1 second to 1.5 seconds, my average rate of change was equal to f of 1.5 minus f of 1 over 1.5 minus 1. And this came out to 40 feet per second. This is a rate of change, so my distance is changing over time. So that's why my units are feet per second. And when I looked at what happened at t being 1.1, my average rate of change was my function at 1.1 minus my function at 1 over 1.1 minus 1. And this came out to 33.6 feet per second. The question is, what happens at t equals 1? Because if I try and find the average rate of change again, I'm going to get f of 1 minus f of 1 over 1 minus 1. And this causes a problem because I can't divide by 0. But because both the numerator and denominator are 0, something fishy is happening here. There might be some common factor that I can eliminate. And so the objective of today's lesson is to figure out what is that factor that can be eliminated. So I want to start by talking about the difference quotient. We've been talking about slope, slope being f of b minus f of a over b minus a. So my question is, what happens when b is a plus a little bit? So this becomes f of a plus h minus f of a over, and this becomes a plus h minus a, and the a's will subtract out, leaving just h. And this is what we call our difference quotients. And so we're going to be using this formula extensively in this course, because this formula helps make the transition between the average rate of change and the instantaneous rate of change. For the average rate of change, h is an actual number, like 0.5 in the case of 1.5 seconds, or 0.1 in the case of 1.1 seconds. Our purpose, though, is to see, okay, what happens if I take the limit as h goes to 0 of my function of f of a plus h minus f of a over h. So if I'm doing this with the problem that we had before, this is 16 times t squared. Well, in this case, t is 1 plus h minus 16t squared, but t is 1 for a, over h. So what I want to do is I want to evaluate the limit as h goes to 0. And in order to do this, I'm going to need to expand this binomial. So I'm looking for the limit as h goes to 0 of 16 times this expression, 1 plus 2h plus h squared, minus 16 over h. And I see a couple of things happening here. One is I'm going to have to distribute this 16. But when I do distribute the 16, this term and this term will form a 0 pair. And of the terms that are left, this 32h plus 16h squared, they're going to have a common factor of h, which is going to be really nice if it factors out and divides out. So I end up with the limit as h approaches 0 of h times 32 plus 16h over h. And this is what we were looking at before. In the previous page, when we were talking about 0 over 0, that 0 over 0 kind of implied that we had a common factor in the numerator and denominator, something that would divide out, and I see that here now. So what I've got here is the limit as h approaches 0 of 32 plus 16h. And now that I have this term, which is approaching 0, I end up with just a 32 feet per second. This is my instantaneous rate of change, which I'll call IROC, as opposed to AROC. Remember that we had AROC when we talked about from 1.5 being our time, we ended up with 40 feet per second. If I dealt with 1.1 second, we had 33.6 feet per second. And when I finally did this 1 second, which I can't substitute, but I can determine it through the limit process, I ended up with 32 feet per second. And I do have this sequence which was decreasing, but coming down, almost converging to this 32 feet per second amount. So, when I find this instantaneous rate of change, this is similar to what we were doing with the average rate of change. Remember that the average rate of change gave me the slope of a secant line. But the instantaneous rate of change is going to give me the slope of the tangent line. And so in the example that we had before, where at t equals 1.1 second, the slope came out to be 33.6 feet per second. I could come up with an equation of that line using the point slope formula. Y minus 16 equals 33.6 times t minus 1. But this was a secant line because it would actually go between 2 points on my curve, even though they were 1.1 units away. And it's very close to a tangent line, but it still passes through 2 points. But now if I take a look at what happened at my 1.0, which I could approximate using the limit process, or I could determine it using the limit process, my slope ended up being 32 feet per second. And because this is an instantaneous rate of change, this actually gives me a tangent line because it only touches at the 1 point. Now it is a little less steep than the previous line, but when I do the equation of the line using the exact same format, this is actually going to be a tangent line. Now remember that when we talked about this in geometry, a secant line was a line that passed through 2 points on a curve. But a tangent line is only going to pass through 1 point on the curve. So that's what we're actually calculating here. Now, there is something we have to watch out for, because just because a line is tangent, and tangent means that it touches a curve at 1 point, that doesn't mean that it's only going to intersect the curve at 1 point. And I have this example here, y equals x cubed minus 3x. This is a cubic function, and because it is an odd function, we end up having this behavior and this behavior. And for reasons we'll discover in chapter 3, I happen to know at this point x equals 1, my instantaneous rate of change is 0. And so that means that my tangent line is a horizontal line. And if all I was looking at was a really small window, I would have no problem with that. But because I know that my curve goes to positive and negative infinity, my tangent line actually pierces the curve in more than one spot. So when we're talking about a tangent line, we're actually talking about a local tangent line. So in other words, it only intersects at 1 point about a small neighborhood or a small interval around x equals a. So in other words, all I really care about is on some interval about this x value, is that the only point that it touches? And I can get it so that as long as I have it that interval or smaller, that situation is going to be true. So we do need to be aware of this, that even though we call it a tangent line, this line may intersect our curve in more than one spot. It's just going to be far enough away that it really doesn't matter to us. So one of the last things I need to talk about is this concept of a normal line. And whenever I say normal, just realize that normal is going to be perpendicular to the tangent line. So in the case that I had before with this parabola, y equals 16t squared, here at t equals 1, there is a tangent line. But if I want the normal line, my normal line has to be perpendicular to the given line. And still pass through that same point. Both of these lines go through the point 116. And from our previous classes, we know that the slope of a perpendicular is the negative reciprocal of the slope for our tangent line. So our perpendicular slope is negative 1 over 32. And so that means that the equation of our line, because it passes through the same point, is negative 132 times x minus 1. And so this is the equation of our normal line. And the key thing to remember here is that when I'm dealing with a normal line, I'm dealing with a line that's perpendicular at a tangent point, perpendicular to the tangent line. And so we'll be often asked to find both the equation of a tangent line and the equation of a normal line. And those of y'all that have a physics background will know that the tangent line deals with velocity and this normal line deals with acceleration. We'll be talking more about this relationship in Chapter 3. So the last thing I want to do is I want to go back to this situation. We were talking about falling. So y equals 16t squared. That was our equation. And after t seconds, we've fallen 16t squared feet. So we now have this relationship that talks about distance, but I can also talk about my instantaneous rate of change, because this instantaneous rate of change actually depends on t. This is actually a function of t, because this limit process, this limit as h approaches 0 of my difference quotient, is really dealing with t plus a little bit minus f of t over a little bit. T is a variable, but I can still do that same binomial expansion, t squared plus 2th plus h squared minus 16t squared over h, and see what happens as h goes to 0. And of course, distributing, this term will go away with this term. Distributing, I can factor an h out of the remaining factor, and I'll have 32t plus 16h. And this is all divided by h as h goes to 0. And so what happens is I end up with a formula for the instantaneous rate of change as a function of t. And that formula is just going to be 32t. That means that the velocity at t equals a is 32 times a. And so in our particular case that we've been using, at t equals 1 second, the velocity was 32 feet per second. But if I'm dealing with t equals 2, then my velocity would be 2 times 32, or 64 feet per second. And I can substitute any time I want into this formula. This formula represents the instantaneous rate of change. And when we took algebra, we noticed that as the time increased, I didn't necessarily have a constant rate of change. But I did notice that this rate of change was increasing at a constant rate. And this number looks awfully familiar. So we'll talk more about this relationship between this constant rate of change of the rate of change and how it's related to velocity, how it's related to the instantaneous rate of change in Chapter 3. But for now, this ends Chapter 2. I'm Mr. Potter. Thank you for watching. Have a great day.